Hello students, how are you? Electric field and electric field intensity. Okay, and also we'll see some numericals related to these concepts. Now, what is electric field? Before understanding what electric field is, just to tell me what is field. This is the problem. In a video lecture, I cannot expect any response from your side, but you think simultaneously with me. What is one field? We are not talking of play field, etc. But my field, your field, these things we are talking. What's a field? Okay. Suppose we are having a magnet. Okay, we are having a magnet. Now, magnetism will study separately, but since you are familiar with the magnets, I am taking up that example here. Suppose you are having one iron pin here. Okay. Now, if you are taking it near, now let us say there is no effect. If I am taking it further nearer to the magnet, nearer to the magnet, nearer to the magnet, from some distance, it will experience one attraction towards it and it will go. So, from what area, if there is a magnet, there will be a space around the magnet within which space the effect of this magnet is experienced, not by everybody, by one iron piece, and that space around the magnet is called the field of the magnet. Clear? So simultaneously, similarly, if there is one static charge q, the space around the charge in which the electrostatic force of attraction and the attraction or repulsion of the charge is experienced by another charge is called the electrostatic field of this charge. Okay. Now, that charge, what is brought nearer is it is used for testing. That's why it's called a test charge, and generally we take the symbol as a Q0. And let us say at the center there is a charge Q is there. Now, what is the force between these two? Assuming that the radius of the distance between these two charges to be r. What is the force between them? We have studied already Coulomb's law, and according to Coulomb's law, that F magnitude of that force of attraction or repulsion is given by 1 by 4 pi epsilon naught Q0 by square of the distance between them. This is the force of attraction or repulsion, right? Okay. Now, this force will not be experienced anywhere. Like last year you had learned gravitation. It was one universal force. It was one universally effect was there because one star is there, and in the millions and millions of kilometers, after millions and millions of not kilometers but of light years, another also is there. Whatever is the distance between them, there will be a force, gravitational force of attraction between them. But in electricity, in case of electricity, that is not so. If this distance goes on increasing and increasing and increasing, a time comes where there's almost no effect at all. So within the field in which this is experienced, in the field, the space around a charge in which the electrostatic force of attraction or repulsion is experienced by another charge brought near it is called the electric field. Do you understand? Now let us understand what electric field intensity is, and then we'll see, it will be clear what's the relationship between them. Okay. Now to make it clear, I will give you one example from day-to-day life. Let us say there is a river. Okay. Now, what is the field of the river? You might be knowing that if the river is very fastly flowing, then we don't allow small children to go near this also, not into the water, but near the river also we do not allow them. Similarly, if one train is moving very fast, we don't allow our children, small little children, to move near it also, because about that also, around that also, there is some effect of it. Along with that, if water is rushing very fast, air also is moving along with that. So about that also, about the River also, before touching the water also, there is some effect, and we may be able to resist that effect, but a small child may be affected by it, may be dragged into that or something like that. Because of that possibility, we don't allow our children. So what I'm saying here is, whenever something is moving very fast, or whatever effect it is creating, it is not only when you come in contact with it, but around it also there is some space in which that effect is being experienced, and we call that a field. Now, in physics, whenever we learn some new physical concept or new physical quantity, the next step is to measure it. We have to measure. For example, length is a physical quantity. Now we are having two sticks, let us say. This is longer or this is longer. If longer, by how many units? How much length it is? What is the, how to measure the length? If I say 1 meter, you understand something. This 1 meter, this is 7 meter. Then it is 7 times 1 meter. Everything idea we could be. So measuring is the next step of understanding of physical quantity theoretically. Okay. So the measurement of electric field is electric field intensity. Let me explain how. Suppose, again I am coming to the same example of a river is flowing. Now, how fastly it is flowing? If somebody is asking this question, how fastly, how you will say? Now see how fastly it is going. If you stand here, what is the force you are experiencing? Is it same if you are standing here? Naturally it is different, right? If you are standing near the river, then also you will experience some force. That is the field strength, or this is another word for field intensity, the electric field strength also it is called. Electric field strength or electric field intensity. Now here, if you are there, you will experience some strength. Here, if you have gone one step deep inside the water, then you will experience some force. The water will push you away, so some force you will experience. You will go little more it will force, because more water is gushing in it. So here the field strength, here the field strength, at this point the field strength at positions, let us say A, B, C, at different positions, the field strengths are different. So how to define the electric field strength or electric field intensity? That must be different from point to point. This is one point. This is one thing to discuss. And even after that, how can we be sure that, let us say at a sea we are measuring, what is the electric field strength in this river example? If you say, how will you say that, let us say Prasant is saying some electric field strength is this much. Rohit is saying electric field strength is something else. Who is saying correct? Prasant is what Prasant is saying, it is correct as per his standards, and what Rohit is saying, that is correct as per his standards. So which is more correct? For example, a lean guy goes and he'll say it's very strong, and a very fat guy goes and he'll go to the same point, he'll say it's okay, it's there is some force strength is there, but it's okay. So whom will we believe? So we can define that the force experienced at sea when a 60 kg guy stands, what the force experienced by a 60 kg guy is standard, we'll say like that. Then only our definition of a field strength is complete, right? You have understood. Now similarly, what will define an electric field is, what is electric field in general we understood, but to measure the electric field strength at different points, what we'll do, a 60 kg guy or something like that, we have to define. Here in electricity we'll define a unit positive charge. The force experienced by a unit positive charge is called electric field strength at a particular point. For example, due to Q, let us say I want to find the electric field strength at a point P, or electric field intensity at point P. Then how will I measure? I will imagine I'll place one unit positive charge there, and due to Q, what force that is experiencing I will calculate, and that force is equal to the electric field intensity at point P due to Q. Clear? If we write these things mathematically, how we say them mathematically. Now this idea should be kept in mind. that we are measuring the electric field intensity due to Q at a point P. Okay, so at point P we placed a unit positive charge. Okay, now if instead of unit positive charge, if there is any charge small q, then what is the force of attraction or repulsion between these two? That is given by Coulomb's law, which is equal to 1 by 4 pi epsilon naught q1 q2, charge 1 into charge q and small q by r square, where r is the distance between the two charges. Clear? So when r is the distance between two charges, we can calculate the force between them. But now we have defined the electric field intensity as the same force experienced by a unit positive charge. That means this q, this small q is 1, isn't it? Then electric field intensity or the magnitude of electric field intensity is equal to 1 by 4 pi epsilon naught capital Q into 1. So only Q remained by R square. Got it? The symbol of electric field intensity is E. Okay. Electric field is a theoretical concept and electric field intensity is the measure of electric field strength, and the symbol of that is E. So E is equal to 1 by 4 pi epsilon naught Q by R square. Now here what is the difference between F and E? Only one Q is multiplied, right? F also is a force, E also is a force. F is a force in general, E is a force experienced by a unit positive charge only, right? So what we can say, F is equal to E, this thing multiplied by Q. Yes or no? So this is a formula, F is equal to EQ, or E is equal to F by Q. Okay, now what is this Q? The charge on which we are measuring the effect of the source charge. This is called source charge, this is called test charge. This is called, these are the customary words what we are using. Why source charge? It's not a question, it's called source charge. Source charge, this is called source charge. And this what we are nearing, that we are bringing near to it to measure the electric field strength, it is called test charge. Now I can say that when test charge is a unit positive charge, when test charge is equal to +1, then whatever is the force experienced only is called electric field strength. Fine. So till here it is clear. But there is one question, and this is one good question. Why test charge is to be taken as small as possible? Why test charge is to be taken as small as possible? Now see, just now in that river example, we had discussed that whoever is going in on his strength, on his own strength, the strength of the river depends in the sense, it doesn't depend on him, but what he says as the measure. If that guy is a fat and a bully guy, then he may say that reverse flow is okay. But if that is a very skinny guy, very weak guy, that guy will say that the force, the strength of the river is too huge or very fast it is, he will say. So what is taken on that it depends. So what is taken in electricity also, whatever charge is taken near the other charge, our purpose is to measure the electric field strength due to capital Q, and we are bringing the small q near to this to do that thing. But when we bring this together, when bring it a closure, this test charge affects the field of the source charge as well. And what we are measuring, that measurement is the measurement of the charge which is already affected. It is not the actual source charge, but it is a charge affected by the test charge. That's why this impact, this effect has to be as small as possible to increase the accuracy of a reading. That is why the test charge has to be as small as possible. So what we can say is, when test charge Q0 is brought near source charge capital Q, in order to measure the electric field intensity at a particular point, there is a chance that the test charge modifies the actual field strength due to the source charge. Therefore, to reduce this effect and determine accurate field strength, the test charge is taken as small as possible. I have given you notes in this. This answer is exactly available. But what I said, if I explain that mathematically, how that will look, E is equal to F by Q only. But in mathematical language, how we write that? E is equal to limit Q naught. As I said you, Q naught is the symbol for the test charge. In general, we are taking Q naught approaching 0, F by Q naught. This is the expression of what I said, that test charge has to be as small as possible. If it is possible, it's near to 0. As near as 0, that's good. That much accurate we will get the electric field intensity. So E is equal to limit Q0 approaching 0 F by Q0. And E is also vector quantity. F is a vector quantity and that is divided by Q. So E is also vector quantity. Vectorially, if we write, we have to write both sides and vector symbol. Both sides. Okay. Or otherwise, if this side is scalar, vector symbols, we can remove both. So magnitudes we are writing. So E is equal to limit Q0 approaching 0 F by Q0. This is the mathematical expression of, we are saying that the test charge has to be as small as possible to get accurate readings. Okay, now to complete this teaching, this of electric field and electric field intensity, we will be taking up a very simple numerical. Okay, now we will take up a small numerical explaining these concepts together. The question asks, calculate force on an electron in a uniform magnetic field of a strength 5 into 10 to the power 4 Newton per Coulomb due north. Now see, why Newton per Coulomb? Again, think of a little rough. What is the unit of see, one thing is, whenever we are learning something new, some new physical quantity, you should, even if it is not said here, you should always ask yourself what is the unit of that quantity and what is the dimension of that quantity. That's a homework. You have to do it on your own, because last year we had studied a unit and dimension on chapter, right? So there we were not knowing some physical quantity also then, but in the second year we will be learning many new physical quantities. And for those new physical quantities, what's the unit, what's the dimension, even if the teacher doesn't raise that in a regular class, you should be asking yourself, and you will be doing that. That will give you a little confidence. So here we have discovered, we have learned one new concept, new quantity called electric field strength or electric field intensity. What's the unit of that? Who will say? Okay, I cannot wait for your answers in a video lecture. Oh, we have already known that E is equal to F by Q. Just now we studied, right? Electric field strength is equal to force divided by. What's the unit of force? It's in Newton. And what's the unit of charge? It's a Coulomb. So Newton per Coulomb is the unit of electric field strength. So that's the thing here. It is saying calculate the force on an electron in a uniform magnetic field of a strength 5 into 10 to the power 4 Newton per Coulomb due north. So towards north there is one electric field. Electric field is a vector quantity, right? So it's having one direction also. Towards north it is. So towards north the electric field is there, and the magnitude of that electric field is given in the question. 5 into 10 to the 4 Newton per Coulomb. Now what is the question? Calculate the force experienced on an electron placed here in that field. Actually for the field I am showing one line only, but there are several lines, right? This is the electric field strength, and in that field if an electron is placed, what force that will experience is the question. Is it clear? So if an electron is placed, what force that will experience is, we can calculate E is equal to F by Q simply. So E is equal to, or F is equal to EQ. What is the force we are calculating? F is equal to EQ. We'll calculate F is equal to E. E is given in the question, 5 into 10 to the power 4 multiplied by Q. What is the Q? Is the charge. What is the charge of one electron? 1.6 into 10 to the power minus 19. So this much. The answer comes minus 8 into 10 to the power minus 15 Newton, and it's a vector quantity. So we have to say force is a vector quantity, so we have to say due south. This is the answer. Now here I have to clarify, and some of you might be thinking already why this is due to south. Now see, electric field, uh, I have to make one video, or I will continue here. The nature of electric field is the electric field is always from positive to negative. That we'll study in detail. I am just saying in short for this numerical only. It's from positive to negative. That means from electric field lines are going from this side to this side. Means it's going this side are some positive charges are there, from positive to negative. You can imagine this way. Now, if direction of electric field is like this, so plus charges must be towards south and minus charges must be towards the north. That's why it is moving from south to north. If plus will be this side, minus will be this side, electric field direction could be in opposite direction. Got or not? Now, if it is given the direction of electric field lines are due north, that means its downside is the positive side and the upper side is negative side. Electric field lines will always move from positive to negative only. Okay. Now imagine one electron placed here. Since electron is negatively charged, that will be attracted towards a plus. Yes or no? So whatever force we are calculating, that is towards south it will be. Clear? So this is this much force towards south. In fact, towards the south, we have to say only minus this many Newton. That only should be the answer. This minus sign represents it is towards the south. We have to say that force is equal to minus 8 into 10 to the power minus 15 Newton, or we can say it's 8 into 10 to the power minus 15 Newton towards south, or the answer we can write 8 into 10 to the power minus 15 Newton towards south. Towards south. You got it, I hope. So it is simply as simple as if a bike is going in this direction, let us say at a 1 meter per second speed. Either we can say 1 meter per second towards west, or we can say minus 1 meter per second is the speed. What is the speed if you'll ask? Either we can say speed is equal to 1 meter per second towards south, 1 meter per second towards west, or we can say simply v is equal to minus 1 meter per second, because we know this minus symbol is for, it is saying that it is towards west only. Fine. Now let us discuss the properties of electric field lines. Now what are field lines first? Let us discuss that. Now again, as I said you already, magnetism will study separately, but while saying these things I am taking up the example of a magnet because from earlier classes you are familiar with the magnets already. Now you remember we had taken one magnet on a piece of paper or something like that, then we distributed one, we spread some sprinkles of iron pieces. Okay, then we started tapping on it. When we tapped on it, everything, all these pieces were aligned in particular directions. Like this. So along some lines, they arranged themselves. You remember this, right? Now, what are those lines? These were called lines of force, I think, in your earlier class. This is only a name what we call lines of force, or we can call these are field lines. Now, in the magnet case, it was always going from north pole towards the south pole, right? Or from where it is coming out, we call that north, and to where it is going in, we call that as south, right? Now, in case of, you are familiar with this example. In case of electricity also, if we are having a positive charge somewhere and a negative charge somewhere, then electric field lines are going always from positive to negative. Now, what electric field lines are? What are these things? Is there lines somewhere where we can touch it? No, it is imaginary field lines. And what are those lines? And now we saw from one experiment that taking one magnetic field, tap it, it is aligning itself. The dust particles, the iron particles, they align themselves into proper lines. And if you disturb them, again you tap them, and those are getting aligned with along the same lines only. That means there must be some effect along those lines, and those are being dragged towards those lines. What are they? Those are nothing but those lines, those imaginary for us human beings, we are not able to see them. Those lines along which this effect is observed is called electric field lines. And if we want to see the effect, if a unit north pole is released, that will be, if a unit north pole is released, and I'm not saying much on that. Unit north pole also is one hypothetical concept, we'll discuss that separately. Now I'm coming only to electric. It is similar to this. I'm not talking much on the magnetic field now. Electric field only I am talking about. Let us say there is a positive charge here, there is a negative charge here. From positive to negative, some lines are there, and how these lines are described physically. Now, if a unit positive charge is kept, a unit positive charge is released here, it will follow this path only. It will follow along this path. If it is allowed to move freely, it will come like this and will reach here. That is, it will be repelled by the positive charge and it will be attracted towards negative charge. But repulse on one side, attraction on one side, along what path it will travel? It will go like this only. Or if we keep the unit positive charge here, it will follow this path only. If we keep the unit positive charge here, it will follow this path only. So these lines, imaginary lines, on which if a unit positive charge is released, which is free to move, follows the path, and that path is called electric field line. And at any point, if you are measuring the electric field strength or electric field intensity, it is nothing but the force experienced by this due to the electric field. What is the direction of that? At that point, if you draw a tangent, that direction gives the direction of the electric field at that particular point. Let us say this is the particular point is P. Here, what is the direction of electric field? There you draw a tangent to the field line. At any point, let us say this is the point P we have taken, let us say P1, P2. At P2, what is the direction of electric field? There you draw one tangent, and that is the direction of an electric field line. So we have understood what electric field lines are. To speak the bookish language, it says this is the path along which a unit positive charge tends to move when free to do so in an electric field. The direction of the unit positive charge gives the direction of the field lines. Clear? This is what we have discussed. But now the thing is, this is a board which is in a 2-dimension. Now in 2-dimension, I am bound to say like this, but the same thing, now you imagine that this positive charge is a ball like, and negative charge is a ball like, that you imagine. So when electric field lines are coming out of a positive and entering into the negative, huge infinite number of electric field lines are coming out of a positive. And this is a ball which is negative, you imagine. Infinite lines, these all the lines which started once, that will be ending in that negative, right? So infinite lines also are entering into the negative and coming out of the positive. Now when it is going in infinite directions, we cannot limit it to one plane, right? How that will look like? See, have you heard last year we had discussed the concept of a solid angle, you remember? Solid angle. What is a solid angle? A ray, position vector, a ray rotates by how much? The measure of that is one angle in 2 dimensions. In 3 dimensions, suppose this is a paper, I rotate it, I make it a cone like this. So how much? This is called solid angle, as simple as this. Okay. So in 3D, when in every direction electric field lines are going through this, how much electric lines are coming out? This will be a solid angle. Did you understand? Instead of just in two angle, you imagine it in the three dimension. So like this, electric field lines are coming out in all the directions. In all the directions, it's entering into the negative side. Now we are going to learn the properties of electric field lines. Properties of electric field lines. Okay, here now we are having some few properties. We will be touching all the properties in short. We'll be discussing, and I have provided already the notes here, and I have started distributing these notes, and after that whoever joined the group, you please contact with your friends and you collect the material somehow. Okay, the videos at one go I have to distribute once again. I hope I'll do that, but other material you please collect. So the properties of electric field lines. The first property is the field lines are always radially outward from positive charge and radially inward from a negative charge. This thing we have discussed already. If there is a plus, this is a minus. Always it is outward from positive charge and inward at negative charge. See, this goes somewhere, it goes and it will come. This goes again, it will come, it will be inward at a negative charge, and this infinite distance traveling, it will be inward to negative charge and outward from positive charge. Field lines of isolated charges start or end at infinity. What are isolated charges? See, in nature, some charge isolated is not possible as long as we think the entire universe to be one block. What I said just now, let me explain you. Suppose you take out 10 electrons from here. So minus 10e you took out, and inside this became plus 10e. Okay. Now this is plus 10e, this became minus 10e. Before taking out this minus 10 electrons, this block was a neutral. Now this became plus 10e. See, E is equal to 1.6 into 10 to the minus 19 Coulomb. That I am not repeating all the time. So whenever we are taking that much of an amount, we are calling that, defining that by one symbol E. So 10E I took out. So this electrons are negatively charged. So minus 10E, and this become plus 10E. But you remember, this was neutral, and if we consider this entire system to be one block, it is still neutral. Plus 10E plus minus 10E is 0. This together, if you will see, it is still 0. But if our idea is, our view is only looking at this block only, this only is our universe now, let us say, this only is our field of observation now, then it was 0 and now it become 10, plus 10. It was 0 and now it became plus 10. Clear? So when we are studying something limited, then the charge is of course changing, but of the entire universe, the charge is not changing. It is remaining neutral only. Clear? So isolated charge means, suppose this minus 10e I will take very far and plus 10e I will take very far. Then this 10 plus 10e will be called isolated charge. Now I am reading that sentence once again. Field lines of isolated charges start or end at infinity. That means here plus 10e is there and this has gone to very far. Where minus 10e is there, we don't know. Then electric field lines will be starting from here and it will end somewhere at that minus. So if plus minus is here, you are seeing that the charge field lines are coming out of positive and ending in negative. Supposing that negative is not there, it is one isolated charge. It is one isolated charge I am having here. So where the electric field line will start in infinite directions, and the question comes where those field lines end. That means infinitely somewhere. How much positive? If a plus 5 Coulomb charge is there, minus 5 Coulomb charge must be somewhere at infinity, and it will go and it will enter into that minus 5 Coulomb charge. Okay, that's what it says when it says field lines of isolated charges start or end at infinity. Fine. So properties of electric charges. The first property we discussed is this. It starts in pictorially I am showing. Okay, this second property we are studying is direction. Now the direction also we have discussed, that plus to minus at any point, what is the direction of electric field intensity? At that point, if you draw a tangent to the electric field line, the direction is nothing but the direction of a field intensity. Field intensity is a vector quantity, so it must be having one direction. And how to get the direction? At which point we want to find the direction, at that point draw a tangent to the electric field line, and that direction itself is the direction of electric field strength at that point. Clear? The third point is third property of electric field lines, which says electric field lines can never intersect each other. Electric field lines can never intersect each other. See, one field line can they ever they can never intersect each other. That's the property of electric field lines. Now logically speaking, why they cannot intersect? Suppose they intersect. Let us say, suppose two electric field lines are intersecting. Then what will happen at the point of intersection? When you draw the tangent to get the direction of electric field intensity, tangent to which electric field line you will draw? At the same point, two electric field lines are going. So if you draw a tangent to this, you are getting one direction. You draw a tangent to this, you are getting another direction. So let us say this point is P. At P, what is the direction of electric field intensity? If that is the question, two direction. This is the direction of the same electric field intensity, and this is the direction of the same electric field intensity. Is it possible? Any vector quantity, if a train is moving, in which direction it's moving means there will be one direction only, right? At the same point, it's moving this side also, this side also. Is it possible? No. That's why, because of this, logically, intersection of a two field lines are never, intersection is never possible. So what I'll say is, the third point is, field lines never intersect. Field lines never intersect each other. Okay, and I said you that field lines are not moving in two dimensions only, and field lines are coming out from positive charges in all the directions and entering the negative charge from all the directions. So better to say, in a pole, let us say, if this is a plus q charge here, from here in all the directions the field lines are going, right? So infinite directions, like this, all the directions field lines are going, and these are infinite in number. I'm just showing 6-7 lines only I'm showing, but you understand that there are huge numbers. Okay, now what is the strength? What is the strength of that electric field? There are two views to look at it. Listen to it carefully. One view is the pure mathematical view, where we said E is equal to F by Q. This thing we said. So at any point, if we are taking some charge Q here, Q we are taking, let us say Q0 we are taking test charge. At any point, if we are taking test charge Q0, then what force that is experiencing? We will find out what force it is experiencing, and that much force divided by Q0 will be the field strength, the field intensity at that point. Clear? Now, this is purely a mathematical view, but another way, Faraday, there was a scientist who viewed in this in a pictorial view. What he thought is the field strength is directly proportional to the number of field lines passing unit area of a cross section, unit normal area of a cross section. Now think, so many lines are coming out of it, and you are placing some small area of cross section through this. Let us say, for the time being, assume that this is square shaped thing, this square. Through this, how many lines are passing? If you take at different points, the number of lines passing are differing, yes or no? Let me explain what I said. Now see, here if I take, let us say this is unit area of cross section, how many lines are going through this? If I bring here, this line is passing this way, this line is passing this way, and through this no line is passing, right? And if I'll bring a little closer, here if I'll take the same area only, how many lines are passing? Two lines are passing through that, yes or no? If I'll bring closer and closer, more and more lines will be passing. At one point, how many lines are passing? At if I'll bring closer and closer, more and more lines will be crossing. When I'll bring it very near, infinite lines are passing through that. Infinite field lines are passing through that, yes or no? Okay. So if I'll bring closer to the charge, electric field strength is increasing, yes or no? So one way is to find out this electric field strength, and the other way is how near it is, the field strength is more. If it's more near and near and near, field strength is getting increased and increased and increased. So what this line says, I hope everybody understood. What this line says, the number of field lines per unit normal area is proportional to the magnitude of a E. The number of field lines, how many field lines are going, if the field lines passing through a unit normal cross sectional area is more, then the field strength also is more. Fine. So fourth point, or what we can say is, in short we can say, okay, I have written for, in short what we can say is number of field lines passing per unit area of normal area of cross section. That's the fourth point. So here is this fourth point. Then the fifth point, since electric field lines cannot intersect each other, they tend to exert lateral or sideways pressure on each other. Now see, there are two properties, next two properties. There are one only as far as the understanding is concerned. How they are one only? We are having in electric field, we had said that like charges always repel each other and unlike charges attract each other, right? Now why that do so? See, if there is a plus charge, there is another plus charge. Now field lines are going away from the plus charge, yes or no? And for this charge, initially these two are very far, let us say. Electric field lines are going away from the plus charge. This also is a plus charge, so electric field lines are going away from it. When you bring these two things closer and closer and closer and closer, what will happen? When you bring it near, now the field line, this field line will try to intersect this field line, and due to another property, we know field lines never intersect each other. So how it will happen when this comes? This will still be like that only. I mean, field lines will be outside only. But these things, if they go, this goes like this and this goes like this, they will intersect, right? They cannot intersect because of another property. That's why what they will do is they will experiencing a lateral pressure. What it says, they will never intersect each other. Gradually, they will become tangential. As they come closer and closer, they will become like this. They will never, one will become like this, another will become like this. One will, this going out is like this, and going out from that charge is this, like this. But these two can never intersect each other. And because of this only, if they cannot intersect each other, if you bring it so closer and closer, a time comes when they develop a lateral pressure. Because of it, we say that like charges repel each other. Clear? So what we can say, in short, the fourth line is like charges repel each other because the lateral pressure developed. So in short, I am writing lateral pressure, and in a very complete sentence, it's given in the note. You observe here, I cannot write, that much space is not there, and that's not required also. And the next property, see, this property is related to why like charges repel each other. Next property is related to why unlike charges attract each other. Another property is electric field lines always tend to contract longitudinally. Contract longitudinally. Electric field lines contract longitudinally. That means, say this is plus here, minus here. Now this is the electric field lines. I am showing only 3, like that infinite are there, many I am showing. So if this lines wants to, longitudinally they wants to contract, means what? When they will contract means become smaller and smaller, automatically plus minus will come closer or not. It is because electric field lines contract longitudinally, unlike charges attract each other. Because of this lateral pressure thing, like charges repel each other. Because of since electric field lines contract longitudinally, unlike forces attract each other. Okay. The next important property of electric field lines are, electric field lines do not form closed loops. Don't form closed loops. Let me explain. Electric fields never form closed loops. What do we mean by closed loops? Let us say there is a plus, there is minus. Now the electric field line started from plus and ended at minus. So from here to here, here to here, it is limited. It's not closed. Closed means if it is going like this and coming, and when it ends where it started, there only it is ending. Then we'll say it is forming a closed loop. From where it started, there only it ends eventually. But electric field lines are not closed from that sense. For example, from positive to negative it is going. From one point to one point it is going. It's not continuing after that. So electric field lines don't form closed loops. That is the explanation of the 7th point. And the final point, in the question you remember there it was given a uniform electric field. Now what is one uniform electric field? The equidistant field lines represent uniform electric field, while the difference in separation between the electric field lines represent a non-uniform electric field. Now see, this is what, from where electric field lines are starting, and if I will show like this at a minus q instead of plus q, it's a minus q. If I take in the same diagram I'm saying, if minus q if I take, what will happen? The field lines all will be inward, right? It will be ending like this. But in between, what happens? From there is a plus q, there is a plus charge. From where it is coming out, there is a minus charge from where it is going in. So from here, if you show like this to there, it is coming like this. So initially or finally, at near the plus charge or near the minus charge, if we'll say, it will be in this nature. But in between, wherever we'll take, the electric field lines will be parallel to each other. You got or not? Now when this case occurs, whenever electric field lines are parallel to each other, we call that one uniform electric field. And when in between also field lines are having different directions from each other, it's called non-uniform field line. So the last characteristic is the equidistant field lines. So what is the property? If the field lines are equidistant from each other, for example, from here to here, what is the distance? From here to here, it's the same distance. Here to here, it's the same distance. Then, but if from here to here it is this much distance, and then it's crowded, and then here again like this, so in this case it is not uniform. So you read this line, then the in short what we can say, the final point is, the equidistant field lines represent uniform electric field. Equidistant field lines represent uniform electric field. Uniform electric field. Okay, till now it's very clear, I hope. So now it's time to discuss some numericals. Now the numericals of assignment 1.2 I have forwarded in the groups. So if you hold the question in your hand, you will be properly following me. Okay, So I am taking up the question of assignment 1.2, question number 11. See, question number 11 is a theoretical question. You can take up for yourself and search in the Google, and you'll get the answer, ready-made answer. I'll be taking question number 12. Okay. A charge plus Q is kept in the inner cavity, and a charge 2Q plus 2Q is given to the inner cell. Okay. A charge 3Q is given to the outer cell as shown in the figure. There is a figure in the question. There are balls. There is one inner ball. See, this is not this much thick. This is not like this. This is one solid ball. This is another solid ball. And the solid balls are having some thickness, right? So let us say this is the thickness of that ball, and this is the thickness of another ball. So putting it. Okay. This is the figure given. Here there is a plus Q charge, and see, there are surfaces. This ball is having two surfaces, right? One is inner surface and one is outer surface. Inner surface is A, outer surface is B. Like that, the bigger sphere which surrounds it also is having two surfaces. One is inner sphere, one is outer sphere. Think of it as a football ball. Inside the football ball also there is one sphere, one surface. It is letter C, and outer surface is D. And also what is given in the question, outside the surface of this inner ball, it has a charge of a plus 2Q. 2Q means plus 2Q only. And the outer surface of the bigger cell is having a charge plus 3Q. Now read the question again. A charge plus Q is kept in the inner cavity, and a charge plus 2Q is given to the inner cell. Okay, inner cell. A charge plus 3Q is given to the outer cell as shown in the figure. Now the question is, find the charges at the surfaces A, B, C, D. Charges at surfaces A, B, C and D. What charges are there? Now in rough I am saying there is a property of induction. Now this induction property is induction property of charge. In general I am saying induction property is you are sitting here, and let us say you are very naughty, and you are always wasting time fighting, quarreling and all those things. You are coming near another child, another student. Then whatever your nature, gradually this guy also will acquire some of your qualities, right? That is called in general induction. If this guy's name is A, this guy's name is B, then if those are brought together, coming closer, they spend some time together, then we'll say that to some extent A is induced by B, and to some extent B also is induced by A. This induced word we are using in day-to-day English, right? In day-to-day language, right? Now in case of electricity, if we bring two bodies closer, let us say if this is having plus 10 Coulomb charge, when this comes near to a body which is a neutral, then what will happen? If it is a neutral, the net charge of this body only is 0, but there are huge number of charges inside. But how many great number of plus charges are there? Equal number of negative charges also are present. That's why the net charge is 0. So what happens when this positive charge is brought A, then since this side is positively charged, equal charges unlike charges attract each other. So this negative charges will come this side and positive charges will move away. So minus 10 Coulomb charge will be developed at this surface which is very near to this, and plus 10 charge, 10 Coulomb charge will be away from this. So what happened here, this entire charge was 0 and now also it is 0 only, but they were mixed, they were remained uniformly everywhere, they were distributed, but now this happened that minus 10 Coulomb and plus 10 Coulomb in the same body remaining only one side it became. This phenomenon is called induction. Okay, now you understood this property. Depending on this property, this question is, if there are two cells here, A, B, C, D, what are they? You have understood, right? A is the inner surface of this cell and B is the outer surface of this cell, and C and D are inner and outer surfaces of the bigger cell. In the cavity of the inner cell plus Q charge is given. It is given in the question. Now what will happen? What will be the charge on A? Now since a plus charge is near to this, minus charge will be developed due to induction. Yes or no? Let me show that with a different color. So if plus Q charge is near, since the plus Q charge is near, by induction minus Q charge will be developed on the inner surface of A. Now this inner surface, outer surface together is one object, right? That inner cell. That's why since minus charge is coming towards it, plus charge will be developed outside the cell. And how much minus charge is there? That much plus charge only will be there outside, because the total charge has to be neutral. So if plus Q is there in the inner surface, there is minus Q charge is there on the inner side of the cell, that is A surface, and on the surface B there will be plus Q is there, right, according to this law. So plus Q is developed due to this induction property, and plus 2Q was given already to B, surface B. So what is the charge on the surface B? That is plus 3Q, plus Q plus 2Q. So totally plus 3Q is there on the surface. What charge is there on surface A? That is minus Q, right? And on C, what will happen? On C, that is the inner surface of the bigger cell, this is plus 3Q is there. So by induction here, minus 3Q will be developed, yes or no? On C, minus 3Q. And because of this induction property, plus 3Q will be developed outside, yes or no? Plus 3Q will be developed. Plus 3Q will be developed due to induction property, and plus 3Q was given already in the question. So plus 3Q, this induced plus 3Q plus given plus 3Q. So in the outer surface, that is in the D surface, there will be plus 6Q charges. This is the answer to this. Now we will take up the 14th question of assignment 1.2, which says, two similarly and equally charged identical metal spheres A and B repel each other with a force 2 into 10 to the minus 5 Newton. A third identical uncharged sphere C is touched with A and then placed at the midpoint between A and B. Calculate the net electric force on C. Okay, so they repel each other. Identically charged means same charge, like charges, right? Charges will repel each other. They repel each other by a force F, and that F is given to be 2 into 10 to the power minus 5 Newton. Let us say each are having charge Q, and the distance between them is R, let us say. The distance between them is R, let us say, and so above. Okay. Then the force between them is equal to 1 by 4 pi epsilon naught Q1 Q2, Q into Q, Q square divided by R square. Yes or no? Here. And let us make some drama. Whenever required, we will go to that. This is equation 1. Okay. Now, what it says, a third identical uncharged sphere C is touched with A and then placed at the midpoint between A and B. Now what happened? A C is brought, which is another sphere, which is uncharged, which is touched with A and then kept at the midpoint C. And what is the midpoint? Means the distance between these two are now R by 2, and this distance between them also is R by 2. That is the midpoint. But when the C is placed here, before that it was uncharged and it is touched with A and brought here. That means what? Now the charge on that is, the charge is changed now. It is, this Q was there, that is uniformly distributed between these two. This also became Q by 2, this also became Q by 2 now. Right? In this situation, calculate the net electric force on C is the question. In this book, the net electric charge on C is the question. Now you tell me what forces are experienced by C. One force is experienced due to A and it will be repulsive or attractive. Both are of the same nature, that's why it will be repulsive. Then there will be a force C due to A, and there will be a force on C due to B also. That also will be repulsive because the nature of charge are like FCB. Yes or no? It is FCB, force on C due to B. Between FCA and FCB, which will be bigger? See, this is the repulsive force between Q by 2 and Q. So this will be a larger force. This will be a force, repulsive force only between Q by 2 and Q by 2. This will be smaller. So net force on C will be towards A only, right? So now see, let us calculate between these two, and FCB is between these two, right? FCB, what is FCB? FCB is equal to 1 by 4 pi epsilon naught FCB, force between C and B, Q1 Q2 by R square. Q by 2 multiplied by Q by R square, R by 2 whole square, right? So this much is equal to, this is R square by 4 and this comes 2 down. So 1 by 4 pi epsilon naught, 4 pi epsilon naught Q square by 2, and this goes up, Q square by 2, and this R square by 4 goes up. So 4 2's z, 2 4's 2 2's z, right? So therefore FCB is equal to 1 by 4 pi epsilon naught 2Q square, 2Q square by R square. 1 by 4 pi epsilon naught 2Q square by R square. And it is a vector quantity, so let us say FCB direction is towards A. Towards A. Let us continue the drama. That's equation 2. Similarly, now we'll calculate what is FCA is equal to FCA. It is the force between C and A, experienced by C due to A. This is, how much is this? 1 by 4 pi epsilon naught between C and A, right? Q1 Q2, Q by 2 multiplied by Q by 2 divided by square of the distance between them, R by 2 square. So this is equal to what? This R square by 4, 4 goes up, Q square by 4, 4 got cancelled. So 1 by 4 pi epsilon naught Q square by R square. And what is the direction of FCA? It is towards B. Towards B. This is equation 3. Let us see. Now FCB is towards A and FCA is towards B. So what is the net force? FCB minus FCA, isn't it? So net force will be towards A, and FCB minus FCA will be its magnitude. So what from after here, or therefore F net on C at C is equal to FCB minus FCA is equal to, so 1 by 4 pi epsilon naught 2q square minus q square is simply q square by r square. This is the force F net, and it is towards what? FCB, along FCB, that is towards A. So this is the answer, but this answer you have to calculate. How will calculate? To say that I have to adjust here. So let me adjust it here. So from here I am taking here. Therefore, F net is equal to what? 1 by 4 pi epsilon naught. The value of 1 by 4 pi epsilon naught is, or let us keep 1 by 4 pi epsilon naught only. We'll see at the end if it will get cancelled. You remember 1 by 4 pi epsilon naught is equal to 9 into 10 to the power 9. But see, let us, it will be cancelled. Q square by r square. How much is the q square? See, from equation 1, we can find the q square, right? It is a force multiplied by, since this was F is equal to this much, q square is equal to F into 4 pi epsilon naught into r square, yes or no? Answer it. F into 4 pi epsilon naught, F into 4 pi epsilon naught into r square. So this is 1 by 4 pi epsilon naught q square, 1 by 4 pi epsilon naught q square, this much is q square, divided by r square, See, you got numerical should be done this way. The calculation will do finally. That's why we need not do so many calculations. See here, 4 pi epsilon naught got cancelled with this 4 pi epsilon naught. R square got cancelled with the r. So F net is equal to simply F it remained. And that F is given in the question already, 2 into 10 to the minus 5. 2 into 10 to the power minus 5 Newton, but towards A. That since it's a vector quantity, we have to write towards A. This is the answer to this question. Clear?